now that you guys have taken a look at how to um, read and interpret position time, velocity time, and acceleration time graphs, we're actually going to come up with the equations that describe those graphs. To do this, we're going to look at a few graphs and use the relationships we know about areas and slopes to come up with our three main kinematic equations. Now, when you hear me say kinematic, kinematic is just the study of motion. Okay? So we're not interested in why things move yet. We're just interested that they're moving. We want to be able to predict where they are at a certain point in time, or how far they've gone, or how fast they're going. Okay, so we're going to start with the case of constant acceleration. This is an acceleration versus time graph. Remember, acceleration is measured in meters per second, or meters per second squared. Time is measured in seconds. And the area under this graph gives us our change in velocity. Now, since area of a rectangle is base times height, the height is a, right, acceleration. The base is time, t, so the area of this graph is really a times t. Now, because this graph starts at t0, a lot of times our initial velocity vi is written as v naught, right? So initial velocity vi could also be v naught. That 0 is saying time 0. Final velocity could actually be any velocity in here, right? Any velocity after 0. So if I want to know how fast I'm going at this time, then this would be v here. If I want to know how fast I'm going at this time, then v would be here. Okay, and the further time goes on, or the longer time goes on, the bigger the change in the velocity, because the longer we've been accelerating. Okay, so we put this all together and we say area is change in velocity, which is final velocity minus initial velocity, but the area of that graph is acceleration times time. So we end up with this equation: the final velocity of an object traveling with a constant acceleration is equal to its initial velocity plus acceleration times time. If you'd like, you can also write this equation like this: the final velocity is equal to the initial velocity plus the acceleration times the change in time. And this way, it makes it clear initial, final, and the time between initial and final. Okay, either of these are fine. They're actually the same equation. Okay, that's our first kinematic equation. Our second kinematic equation goes to the next graph, right? We start with acceleration to find our change in velocity. Now we're going to look at a velocity graph to find our change in position. Okay, this velocity shows a constant acceleration, right? Our velocity started here and it slopes up. It's getting faster. Okay, so we have a constant positive acceleration. Now, you guys, I'm sure all remember from algebra that the standard equation of a line is y equals mx plus b, where y is your independent variable, x is your dependent variable, m is slope, and b is your y-intercept. Okay, well, if we sub in the values we know for velocities and slope into that equation, we get our velocity, right, our y variable, is equal to mx. Well, m is our slope, which is acceleration, right? The slope of a velocity time graph is acceleration, times x, but our x variable is t, plus our y-intercept. Well, that's where it started. That's our velocity at the beginning, or v naught. Okay, so the equation of this line is really v equals acceleration times time plus v naught. Okay, now the area under this line is actually composed of two parts. There's this rectangle, okay, and there's this triangle. Now I want you to notice something. If there was no initial velocity, if the object had started at rest, then this rectangle would have a height of 0, and therefore its area would be 0. Okay? If there is an initial velocity, then it's got an initial area as well. Okay? So what we want to do is we want to figure out the area under this graph, because if we know the area under this graph, we know the change in position, right? Delta x. Now, that's final position minus initial position, and just like we did with velocity, we can do this with position as well. So if you see x or x naught, those are also considered final and initial. Okay, position at the start time, position at the end time. Now what we want is we want to come up with the equation for this area. Since that's a rectangle, that's base times height. Well, the height of this rectangle is our initial velocity plus its base, which is t, or not plus, times its base, which is t. Then we have to add on to that the area of this rectangle or triangle. Okay, now a triangle's equation is 1/2 base times height, so 1/2 the base is still t. The height, though, well, the height of this triangle is dependent on what time we are picking for the end. Okay, And so the y value, or the height right here, this v is equal to the acceleration times the time plus our v naught. But we've already taken care of that one, so all we have left to deal with is acceleration times time. Okay, so plus 1/2 t times at. Well, if we simplify this, okay, and that's what we're going to do down here, we know the area, which is really the change in position, is equal to initial velocity times time plus 1/2 at squared, right? That's time squared. Now, we're going to go ahead and substitute delta x for this, and so what we get is our change in position equals, and I usually write it this way, it doesn't matter though, 1/2 at squared plus v naught t. Okay? It doesn't matter what order you write those in, but this looks more like a parabola to me, so I write it like that. Now, just a quick dimensional analysis on this to make sure this equation makes sense. Delta x, that's a change in position, so it's measured in meters. That's just a number, so we don't have to worry about the half. Acceleration is meters per second per second. Time is seconds, but it doesn't say time, it says time squared, plus initial velocity. Velocity is meters per second. Time is seconds. So did these work? Well, that second cancels that second squared cancels that second squared. So we end up with meters equals meters plus meters, which is perfectly legitimate. Okay, so dimensionally this works, and algebraically it works as well. Okay, this second kinematic equation, we use this equation a lot. Okay, comes into a lot of them. Now, we're going to take these first two equations, the main two kinematic equations, and we're going to use them to come up with a third equation that doesn't involve time. This equation is incredibly valuable. So we're going to do this once. We're going to derive it. We're going to see where it comes from. Then we're just going to use it, so we don't have to keep using it, keep figuring it out over and over again. Okay, so what we're going to do is we're going to take our first kinematic equation, final velocity equals initial velocity plus acceleration times time. We're going to solve this equation for time. Okay, so to do that, we're going to subtract v naught from both sides. So v minus v naught equals at. And then we're going to divide both sides by a, and we get time equals our change in velocity, v minus v naught, divided by acceleration. Okay. Now we're going to take this equation and we're going to plug it into our second kinematic equation. Now our second kinematic equation said our change in position, okay, equals 1/2 at squared plus v naught t. Okay, now everywhere there's this t, we're going to go ahead and plug in this equation. Okay, so this is actually a strategy we use a lot when we have multiple equations, multiple unknowns. Okay, we take one, solve it, and plug it into the other. Okay, so let's keep everything straight and do this in a nice orderly fashion. Delta x equals 1/2 a. Okay, now I'm going to sub in v minus v naught over a. But remember, this t was squared, so I have to square this. Okay, and then plus v naught times t, which is v minus v naught over a. Okay, so all I've done is I've replaced the t with this equation that represents t. Now we're going to go ahead and we are going to simplify by squaring stuff out, distributing things across. Okay, so delta x hasn't changed. 1/2 a, not going to do anything with that yet because this parenthesis has got a big square on it. Okay, and remember, when we square this, I'm going to write this out over here, that doesn't mean square everything in it. That means take v minus v naught over a times v minus v naught over a. Okay, so we got to FOIL these together. Okay, so first times first is v squared, outside times outside is v minus v naught, inside times inside is v minus v naught. So minus 2v v naught, or v naught v, and then the last times last is plus v naught squared all over a squared. Okay, then we have to add on to that this last term plus. Now this v naught actually distributes in there, right? So I have v naught times v minus v naught times v naught. So that's actually v naught. squared, and this is still all over a. Okay. Now we're going to simplify this term. We're going to distribute this half in this a and see what we come up with, and then we'll see if we can get like terms and see what drops out of this. Okay. So we have change in position, delta x equals 1/2 a times this whole thing, but this whole thing has this a squared in it. So I'm going to cancel that square with this a, and then I'm just going to go ahead and distribute that half through to everything. Okay, now remember this a is still left and it's dividing everything. So this first term becomes v squared over 2a minus this half and this 2 cancel. Okay, so minus v naught v over a plus v naught squared over 2a plus v naught v over a minus v naught squared over a. Okay, so we have a lot of things that are over a, which is good, so we're going to be able to combine some terms. First thing that I notice jumps right out at me, negative v naught v over a, positive v naught v over a. Those two cancel, they're gone. Okay, I do not have any other v squared, so this term is going to stay. I don't have anything I can do with that or combine with that. I do have a v naught squared and a v naught squared, so I'd like to combine these terms, but this one's over 2a, this one's only over a, so I have to have a common denominator, so I'll just multiply by 2 over 2, and then we can combine these terms. So let's simplify this again. Delta x equals v squared over 2a, this term's gone, plus v naught squared over 2a, this term's gone, minus 2v naught squared over 2a. Okay, so this equals, okay, I can combine these two terms, so I have v squared over 2a minus, right, 1 minus 2 is negative 1, so minus v naught squared over 2a, okay, equals delta x. So we're going to simplify this one more time, maybe 2 more times. Okay, so I have delta x equals v squared minus v naught squared, and since these have a common denominator, I can put them over that denominator, 2a. Now I can multiply both sides of this equation by 2a, so I get delta x times 2a equals v squared minus v naught squared. Then I can add over that v naught, and I get final velocity squared is equal to initial velocity squared plus twice the acceleration times the change in position. This is the third kinematic equation. Okay, this is not new necessarily, but what we've done is we've combined the first two and eliminated time, and this equation comes in incredibly handy. We use it a lot. Okay, now it is important to notice that this is not velocity, it's velocity squared. Okay, and don't lose that square sign or it will mess up your math. Okay, so the next thing we're going to do is we're actually going to take a look at how to use these equations. So the next video shows us how we use these equations to solve kinematics problems.